SwayamPrabha. Digital India. Educated India.
Welcome back. In module 5, we will talk about water supply distribution system and plants, and in lecture 21, we will be specifically talking about distribution systems and their layouts. So, the different concepts that we will cover in this particular lecture will be on distribution system basics or fundamentals, zoning, hydraulic performance and network model, pressure in the distribution system layouts, and valves. So, now that we have covered a large part of water supply services, for example, we have talked about the different intakes, then we have designed storage facilities, the storage reservoirs, we have also talked about pumps, and we more or less have we are now ready to actually distribute the water to the targeted areas or to the residences or to the urban area. Now, when we are talking about distribution, that involves pipes and water flows along a single pipe, of course, but we also have to take it in the context of the layout of that overall pipe network. So, we will learn both about the overall network as well as how to calculate the different parameters like pressure, velocity or the slope of a pipeline. So, these are all things will be discussed, and along with also what kind of pipeline, what materials are used for pipelines, how to select pipes and so on. Okay. So, talking about distribution system fundamentals, of course, after either drawing of water or treatment of water, water has to be carried to the treatment plant in case we are drawing the water from a river, or to the service area if in case we are after treatment we can take the water to a service area through means of conduits or pipes, and this is called conveyance of water. Now, pipes or channels, we can say also conduits could be both pipes as well as channels, right? Open channels, open ducts, this kind of things could be also utilized. So, first of all, if a source is at a higher elevation, that means whenever we are taking water from one point to another, if the source from where we start taking the water, if it is at a higher elevation, then water can flow under gravitational flow, or if it is not at a higher elevation, that means, or rather the elevation is not that high, then we can also pump the water. So, that means we can use a pump to create that extra pressure, so that the water is pushed and then sent to the point where it is supposed to be sent or where it is supposed to be distributed. So, in that case we will use a pump. So, either it could be based on gravity or it could be based on pump, and sometimes we also use the pump to raise the water to a higher level like a overhead tank, and from there the water again flows into the surrounding area or the distribution area via gravity. So, this kind of systems are there. Now, whenever we are talking about conveyance of water, in most cases it is a pipeline, that means it is a closed conduit, but sometimes we also go for open channels as well, and in case of open channels, it is almost like a normal canal, or you can say that it is like a drain. So, there, since water because it flows due to gravity, and we need to give a uniform longitudinal slope. That means, as much uniformity could be possible, we would try to provide that. And we will make sure that the hydraulic gradient line, which you have learnt in the previous lecture. So, we have the hydraulic gradient line wherever the piezometric, based on that piezometric surface, and then we know that wherever, at whatever level the water is available, and at wherever this line touches the channel, and we would try to maintain the water level at those particular levels. So, so in case where in case of pipes and all, we don't need to bother about that, because pipes are closed conduits, and because we would be putting pressure into the pipeline, it can either go above or below that hydraulic gradient line. But if it does so, then automatically the pressure in the pipeline will increase, and that needs to be also taken care of either by providing a more thicker conduit or by providing a larger conduit and so on. So, carrying capacity of water main, that means the water main pipeline, depends on its size, velocity and the pipe characteristics. So, that means the quantity of water or the carrying capacity of water through a pipeline of course depends on the size of the pipeline, the speed at which it travels, and also on the certain characteristics of the pipeline that we will learn eventually. Now, in most cases we will try to maintain a fixed range of velocity. Why? Because if the range is not fixed, then what happens? Sometimes if the speed is too high or the speed is too low, then it will create other problems, such as it could create scouring of the pipelines. It may lead to different issues of friction, longevity, and all these things come into play. So sometimes, in most cases, we will fix a range of velocity and we determine the size of the pipes to meet the demand of water. And when we say demand of water, we have to consider the peak demand, because we are laying the pipeline which would be able to take care of both the peak and non-peak periods, and that basically means the pipe has to be designed for the peak period. So even though demand, whenever we estimate demand, it is based on average demand, but we need to estimate the peak demand first and then determine the pipe sizes that should be provided. Now, pipe material is chosen based on pressure developed in the pipeline. It depends also based on friction and the longevity of the pipeline. Plus, there are so many other factors that we will discuss later on. And whenever we choose a pipe, that means what kind of pipe we are going to use for a particular case or a particular context, it depends on the quality of water, it depends on the quantity of water that we are going to transport, it depends on the pressure in the pipeline, it depends on the velocity of water. So these are all the parameters that are considered when we choose a pipe. Now, when we choose a pipe is basically done because there are different materials, different diameters of pipeline, each has got their ratings and standards, and we have to check those standards and ratings to find out which one is the appropriate pipe for our context. Okay. So when we talk about distribution system, there are primarily three types of distribution system. So the first type is the gravity system. So you can see in this particular image, we have a source which is at a higher level. So over here we have a reservoir, and we can see that it's at a much higher level, and the supply area is around over here. So maybe we have some buildings or some urban area over here. So the pressure that is required at this point where the supply has to be done, it has to be in such a way that the design of pipes are done so that the water head at the consumer is just the minimum required, and the remaining head is used to overcome the frictional losses in the pipeline. So that means at the end we require some amount of pressure in the pipeline. Why? Because we want the water to go up to a certain height, because if it's a 3-story house or a 6-story house, the urban the ULB body or the municipality may decide that okay, we want a water pressure which will be where it would be able to reach without any pumping or anything directly to the 6th floor or directly to the 3rd floor. So that is the amount of pressure that has to be there once the water reaches at that point. So obviously the total pressure that is required is the pressure which is required at the delivery point plus the pressure that is required to overcome the frictional losses in the pipeline. Now, why frictional losses? We will talk about that later. So that is in case of gravity system, there is no requirement of pump, and if you see that this amount of pressure which is H plus HL, HL is because of the loss the pressure due to this friction. HL is the one that has to be overcome. Now, during different demand periods, of course, the pressure would be different because water is not the volume of water that is required is different in the different peak periods, and so the travel of water would also be less. That actually results in less amount of water to be less amount of head loss, right? So HL is basically head loss, or the head that is required to overcome the frictional losses. So HL plus H is the amount of pressure that is required in the system, or that is the pressure that should be available based on the height of this particular reservoir. So, the more the height or the more the water level of the reservoir at a higher level, more is the pressure available in that particular system. So, this is the gravity based system. Then we can have a dual system or a combined gravity cum pumping system. So, as you can understand, there is a pump involved as well as there is the gravity system, that is we are also employing gravity as well. Now, how we can do that? In this system, pump may be connected to mains as well as to the elevated reservoir. So, that means we have a pump house using which we are lifting water to an elevated reservoir. From there, we are again distributing the water. So, we are actually creating that pressure head over here, which is required to serve this particular locality. So, we have H plus HL is being taken care of by pumping the water directly into the overhead reservoir via this particular pump. So, this is a system where we are just using a pump to lift the water, but maybe the entire water could be pumped to the elevated distribution reservoir from where it is distributed using gravity, but sometimes during heavy demand or the peak demand. Now, in that case, flow in the distribution system may come both from the pumping station as well as the elevated reservoir. So, as you can see that during the peak demand period over here, you see the head loss increases. So, that means in this case we require to put some extra pressure. If our initial pressure is lower, for example, we give an initial pressure like this, then that means we need to give that extra pressure to actually make sure that the distribution during peak period is also adequate. So, in that case, we will also operate the pump which is directly connected with the distribution network. So, pump will create that extra pressure in the pipeline. So, together with the pump as well as the overhead reservoirs, the head, that together overcomes the requirement of pressure at the distribution area. So, water stored in the reservoir meets the requirement of demand during pump breakdown and pump firefighting. So, that is also taken care of. And finally, we have the system, it is a pumping based system, that means water is directly pumped to the mains, there is no overhead reservoir involved. So, different pumps are used to meet demand at different times of the day. So, that means when we have discussed pumping, we have talked about multiple size pumps in a particular pump house, and during at different demand periods we operate different kinds or different number of pumps, right. So, that is the system that is being employed, and sometimes variable speed pumps are also used, but of course, these are much more costly. So, these are the three kinds of system that are there, but of course, out of all this you can understand the gravity based system is the most efficient and reliable, because there is no failure in case of gravity, but there could be failure in the normal pump, right, either failure due to electricity or failure due to other reasons. So, whenever we are selecting pipelines for designing this network through which the water is transported from the overhead reservoir or from that pump house to the service area, in that case we should design the network in such a way so that we avoid pressure surges and we avoid non-standard pipes. So, that means we should use uniform size pipelines. Of course, it is not the same size pipeline used in the entire network, but along the main we will go for same size pipelines. And we also make sure that there is unnecessary pressure surges are not developed. And then one benefit is if we have multiple raw water sources, then we can have from different directions we can have we can take care of the service requirement or water requirement of that area, and that actually reduces the length of pipelines. Similarly, and obviously long distance pumping should be avoided, because that requires a lot of energy that goes into the pumps, and then pumps with low heads to avoid pressure surges, and pumps with high pressure rating should be used. So, these are the two typical strategies that we use. That means, we use pumps with low heads, and because if the head is high, then suddenly when the pumps are stopped, these surges happen. So, that means whenever a pump is operating in a system and then we suddenly stop the pump, then this pressure surges build up in the pipeline, and pipes with higher pressure rating should be also used. So, because of the efficiency rating, we have talked about that in earlier lectures. So, the next most important thing is zoning, and when we talk about zoning, we are talking about either district meters area or pressure managed areas. So, what is zoning? So that means whenever we have an urban area or an area where we need to supply water, we usually divide the area into zones. Now, there are several ways to do that, and there are several criteria that has to be fulfilled when we do zoning. But at the same time, this zoning is nothing, it's not like there is only one outcome. There could be many variations of zoning for a particular urban area, and overall we have to test the efficiency of the zoning that we are proposing, and there is no one solution. There could be many solutions, but more or less we would like to follow certain strategies. Now, what does zoning helps? Now, zoning helps in equalization of supply of water throughout the area. And what does equalization means? There is pressure and the discharge. Now, why equalization fails? Whenever we have a very large area to serve, of course, the water starts far away, then it reaches the service area, and within the service area also it has to travel a lot. So, the pressure available at the beginning of the service area and the pressure available at the end is not the same. So, the pressure gradually falls down. So, at the first part, maybe water will be able to rise up to 6 stories, but at the last water will be able to rise only 2 stories or 3 stories. So, that means there are some problems in that. Then the quantity of water that has to be sent, then if the faraway area requires more water, then the diameter of the pipelines would be unnecessarily larger earlier. So, many issues are there which could be actually, we can reduce the overall length of pipelines, we can reduce the diameter of pipelines either by doing proper zoning. So, pressure and flow drops at some places happens when size of the distribution network increases. So, this is one issue that we are trying to overcome. And then there is issues of demand and leakage management. That means we need to understand how much water is being supplied to a certain area, and if there is leakage developing in a certain part of the system, right. So, if the area is zoned, we have an idea about how much water is going into the zone, because these areas are metered. That is why it is called a district metered area. That means water enters and goes out, whatever. If it goes out, of course, it may not even go out from that area. In that case, we have meters at both the entry and exit, so we can measure how much water is actually getting in. Similarly, if there is a fall in the pressure in that particular area, we can understand some leak is happening, but other areas are fine. But if this kind of zoning was not done, it would have been very, very difficult to find where the leak has happened, right. So, that is why we need to do zoning. Now, how do we do zoning? What are the criteria? There are several criteria. Some of these are the density of population. Of course, areas where a lot of people live, that means the zone size would be smaller. Type of locality, is it a commercial area, is it a neighborhood, residential area, depending on that we may actually zone. So, sometimes even though the mathematically we can say that a neighborhood, 80% of the neighborhood should be one zone, but we may not think that okay, another 20% we can add. So that the entire neighborhood falls under one zone. So, it also follows the administrative or other sort of boundaries that we have in mind, right. Then the topography. So, for example, there is a river passing through a particular area, we cannot have the distribution network on both sides. So, or also if based on the contour of that area, we can also decide on the zones that has to be provided, because if there is a hillock in between that area and we have to supply water, and probably it is better to make that hillock into a separate zone. Why? Otherwise, the pressure difference between the hillock top and the surrounding area would be too high, and it is better not to put that kind of pressure difference within one zone. So, similar hydraulic, so we usually try to follow that the hydraulic grade line is more or less at similar levels, and within two zones elevation difference of 15 to 25 meter is possible. So, that means in case of very flat terrain, of course, this is not possible. That means we do not have that much elevation difference, but elevation difference of 15 to 25 meter could be considered, but also we can consider the height of the buildings and to what height we want to send the water, and all these things also play a role. So, to maintain similar hydraulic grade line within a zone, we have to make sure that different zones are at different, we separate two zones based on their elevation difference, and separated from surrounding zones by pump and control valves to control pressure, flows and leaks. So, that means each zone could be separated. That means water supply to each zone could be controlled. So, if we want water supply to be stopped for a particular zone for repair work or for extension work, we can do that. So, for that we usually have control valves or boundary valves using which we can create, we can stop or prevent water to go out of that zone or to come inside that particular zone. And this helps us to control the pressure, flows and leaks and so on. So, also different zones may have different pumps to catering to that particular zone. So, that is also another reason. So, we usually have flow meters which are installed in the distribution main at the inlet and the exit of the district metered area to monitor consumption and to detect leakage, as we have discussed earlier. So, there are different kinds of DMAs. We can call it a single inlet DMA, that means only one water comes in and then it is distributed into the entire zone, one main line comes in, or it could be multiple inlet DMA, so where lines from multiple direction comes in and it serves different part of the DMA. And then it could be a cascading DMA, that is water comes to one DMA, then from there this DMA it goes to the next one and then to the next one and so on. So, this kind of designs are there, but each one has got, when we would learn in detail about the distribution network, you will see that there are different kind of systems, loop system, non-loop system. So, in that case, maybe the calculations for pressure in a pipeline or what should be the size of the diameter of the pipeline, all this becomes more complicated and it needs different strategies to solve those kind of networks. But we can do that because there are some benefits to it as well. So, when we learn the different types of distribution system, we will focus on that. So, what would be the zone sizes? Zone sizes are around 1000 to 3000 connections, but sometimes, as I was saying, that 80% of the neighborhood is covered, another 20% is to be added. So, we need to have some leeway as well. So, standard is 1000 to 3000 connections, but sometimes we can even go up to 5000 if required. So, this entire process of dividing this entire area is an iterative procedures. And that means once we know that okay, this is the proposed zone based on all the different criteria that we have discussed, we can determine the network for that particular area. We can do assumptions regarding pipe sizes, and then we can test the hydraulic performance. Now, what does hydraulic performance means? We will see that based on our design, we can use a software, or mathematically also we can do it by hand, but because it's a very complex network, it's very difficult. So, nowadays we use softwares, and there what we do is we run the software, simulate the entire supply during peak period, non-peak period and all, and we see if the pressure is exceeding in certain nodes or at certain points, and those has to be rectified, or maybe we have to change the diameter of pipelines and so on. So, we need to test the hydraulic performance once we have done the zones, and then we can even optimize and find out that what should be the best possible way we can zone that area, so that overall the costing of pipelines and all these things could be lower. So, this is how we design this network. And some things that we may consider, that is we can have more than one storage tank per pressure zone, and of course, it depends on the distance or the spread of that zone, because if the spread is too much, it is better to have multiple tanks, and this increases system reliability and the distribution time. The reason is, if there are two tanks, of course, when one fails, the other can supply, because all the network is connected, and the distribution time is because if you are putting two tanks, obviously you reduce the length of pipelines and all, and overall the distribution time reduces. Neighboring zones are interconnected for emergency supplies, but separated by valves which are kept closed. That means, as we are discussing, valves are used at the boundary to prevent water to go from one zone to another, but if we want during emergency, we can supply water from one zone to another as well. So, that is why those valves could be also opened if required. Then loop lines are preferred since multiple directions can be covered. So, we were saying that multiple inlets and all this. So, we can have loop lines instead of a single line going to an area then serving area, this thing. We can have if in this particular area we can create certain loops. That means water could be sent from this side and this side to serving this particular area. So, we can create different loop networks. So, we will discuss that later in the later lectures. And some same pressure in a zone ensures infrastructure design in the same design criteria. So, we will see that the maximum difference in pressure is around 3 to 5 meters not more than that, and that will actually help us to make sure that the pipe sizes and all these things are more or less uniform. So, if it is beyond that, that means we have to be, there will be a lot of pressure difference in this particular area, and for that the pipe designs and all these things needs to be different. And then valves at the zone boundary only and not at the building level, and pipelines are designed considering mostly acceptable velocities during peak flow, since head loss is usually minimum. So, that means acceptable velocities has to be determined, and during peak flow head loss is usually the overall head loss is minimum, that not that high. So, mostly it is based on the velocity we will design the pipeline. And water distribution, overall we see that the overall each pressure zone, the total head that we have to take care of ranges from 92 to 231 feet. So, roughly around I think 139 feet. So, 139 feet is the range of pressure that is provided to a particular zone. That is that, of course, we will try to be within that particular range. So, this is the range within which we need to keep the pressure in the water, because if we go beyond that, then there are other issues that involves. So, head loss plus pressure gradient difference together is this 139 feet. So, water distribution system within each pressure zone typically ranges from 92 to 231 feet of head for all service connections. So, that means when we consider all the service connections in that particular zone, all the 3000 connections, overall this is the amount of head that we actually provide. So, district metered areas DMAs, we actually metered both the inflowing water and the outflowing water. Pressure can also be regulated if required, and we can do a water audit. That means we know exactly how much water at what time of the day that is being supplied and how it varies from season to season and all this. Then we can control water loss, because leakage detection and all these things are much easier. We can also determine the age of water. If the distribution system is such that the water doesn't comes back, that means it becomes stored at certain sections or certain pockets of the network and it becomes stale. So, we need to remove that water. So, that is so we understand the age of water, we can model that part as well. So, all these things could be done. It's very difficult to do by hand. So, we nowadays use software models. So, we need to determine the delivery pressures at different pipelines. So, based on the suggested pipe sizes, pipe material and all this for a particular area, we determine the pressure in different pipelines in that particular design, and for that we use softwares, different kind of softwares are available, and this hydraulic model simulation for flows corresponding to average day, peak hour with a fire, and all these things are conducted to determine the appropriateness of the design that we suggest. So, two popular softwares, Bentley WaterGens, which is a commercial software, and then there is EPANet, EPANet you can also call, which is a free software. It's US designed by the Environmental Protection Agency. It's the most widely used software, and it's very easy as well. So, you can see the interface. We will discuss that in our final lecture of this module. We will discuss or demonstrate this particular software, how to do that. But you can see in this particular image, there is a source, there is a pump, then there is the network, then there is a loop over here, and then there is a tank. So, if we can design a network like that and we can put in the demands at each of these particular points, and we know that how much water is drawn during peak hour and all, and then we can lot of other information needs to be entered, the pipe invert levels and all the different things, the pipe diameters and all this, and together then we can run a simulation and we can determine if the pressure is exceeding at certain points, and from there we can make corrections and all, and that is how we more or less design a pipe network. So, what kind of pressure is there in the distribution system? So, up till 3 stories, 2.1 kg per centimeter square of pressure is required. if we want the water to reach up till 3 stories, if we want it to reach up till 6 stories, then we go for 2.1 to 4.2 kg per centimeter square, 6 to 10 stories 4.2 to 5.27 kg per centimeter square, and even above 10 stories it's more than 5.2 or it's 5.2 to 7 kg per centimeter square. So this is the kind of pressure that we require in the distribution system if you want to reach that kind of a height. And the main lines are designed to carry 3 times the average demand. That means, or sometimes based on, you can also estimate that previously we have discussed 1.5 times, then 1.8 times based on hourly maximum demand and so on. So we can go with that as well, but usually the main lines are designed to carry around 3 times the average demand. Service pipes, that are the branch pipes, are designed to carry twice the average demand, that is 1.8 times. Instead of that we can go for twice, and minimum velocity in the pipeline is designed as 0.6 meter per second, and the maximum is more or less designed as around 3 meter per second. So this is the range within which we have to keep our velocity, and based on that we can use different diameter of pipelines. But even though this is the range, there are certain recommended velocities which we should adopt for different diameters of pipeline, because that will result in optimum cost and optimum efficiency of those pipelines. So for 10 centimeter diameter pipeline, the recommended velocity is around 0.9 meter per second, whereas for a 40 centimeter diameter pipeline, the recommended velocity is 1.82 meter per second. So that is still within this 3 meter per second limit. So now we will discuss about the different kinds of distribution system. The first one is a dead end or tree system. As you can see from this particular image, we have this main, this is the water is coming from this direction, and then we have arteries coming out of that, then there are branches, or we can call them submains, and from submains there are branches, and as you can see there are also valves which are put over here. That means we can, when we turn off those valves, then the water will be stopped in this particular section of the pipeline, and then we can conduct repairs and all. But at the same time you can understand, because the pipeline has got dead ends, that means there is a chance that if water is not drawn, that means this houses over there is dilapidated, or people are not living there, or maybe there is no house yet to be constructed over there, but the pipeline is already laid. In that case, you can understand the water becomes stagnant in this part, right, and the water will become stale, and when the water quality falls, it will affect the other parts of the pipeline network as well. So there are so many issues with this dead end system, but at the same time you can understand this is the most convenient system, because as the city grows you can keep on growing the particular network, and in that way it is good, it's easy, the number of valves required is less, but of course the benefits that you get out of other systems like loop systems, that is not possible over here. So I will just quickly go through the points. Most Indian cities show this kind of system, and one main starts from the service reservoir along the main road, and from there we can have submains, and then we can have branches from in both directions. Branches are minor distributions for streets, mostly at 90 degrees maybe, and there are dead ends. System is cheap in initial cost and easy determination of pipe diameter, valve sizes, because it's pretty easy to solve this kind of a network, that you can understand from this, right. So if I know the demand of water over here, I can determine the pumping rate, and if I know the pumping rate, then from there we will teach you how to design the size of pipes. And if the system breaks down, then water is cut off for the entire downstream. So something happens over here, a leakage, in that case we have to stop the pump, water supply, water along in the main, and everything else gets stopped in the other downstream of that particular point, right. And poor water quality, stale water has to be removed occasionally, and mains of at least 6 inches for distances greater than 1000 feet, and lesser number of cut-off valves and pipe length. So that's why the cost is less. You require less number of valves, and the pipe length is also lesser, because you don't have loops, you only go in one direction. So then we have the grid iron, or we also call it interlaced or reticulation system. So as you can see from the image, this is the main line, water is going like that, and we have this parallel arteries also going. Then there are these submains going in this in the 90-degree directions on both sides, and then we have got these valves. See, in each, whenever water is passing, we can stop the water in certain, like we can stop this valve and this valve both these valves, and then we can do a repair in this particular section, right. So, we can use these valves to stop the water, but you also need to understand that if we do so, the number of valves also increase, and that also increases the length of the pipeline, and the total length of the pipeline is also much higher than the previous system. But what is the benefit? So, if I am located over here, my house is over here, I will get water both from this direction and this direction. So, even if repair is happening over at this section, this is closed, then we can still get water from this direction. So, these are the benefits of this kind of a system, and usually we see it in planned cities. As you can see, the network itself is suggestive that it is possible in a grid network setting or setting which is more or less formal setting, or a formal transportation network or road network, because most of the pipelines will follow the road network, and usually installed in cities like planned towns, like in case of Chandigarh, and all dead ends of mains are interconnected and water is supplied from both directions, and most mains are interconnected and reinforced by arterials, as we are discussing. The main line is along the main road and sub mains goes in both directions, and more cut-off valves or slice valves and longer pipes are required compared to dead end system. And because water is carried from different routes, discharge carried by each pipe is smaller, thus requiring lower pump size and frictional losses. So, one benefit is you get the water from different sizes. The other benefit is, because you are supplying water from both directions, the overall the pipe diameters would become smaller. So, if pipe diameters are smaller, then frictional losses would also be smaller, and then the price of that particular pipes would also reduce. But again, we require large, longer length pipelines. Repair is better, convenient, effective in firefighting, because you get water from multiple directions. So, pressure balance is better, and no stagnation of water, and therefore reduced chances of pollution, and good flow is maintained above 6 inches if the pipe diameter is given more than 6 inches, and costlier and difficult to design. So, this we will, when we design in the final lecture of this module, when we design a network, you will see that this kind of networks are much difficult to design compared to a simple tree or this kind of a dead end system. So, then we have got this arterial loop system, also known as within that we can have circular or ring system, and also the radial system. And in circular or ring system is almost similar to the grid network, but the difference is we have the main, this is the incoming water and this is the outgoing water, and this goes along the sides. Instead of going along a main in the middle, it goes along the sides in both directions, and then water is supplied from here. Using this network that we design in between, we can supply the water to the different zones. Now, what is the benefit? The benefit is water is not only supplied from 2 directions, water is supplied from 4 directions in this particular case. And the other benefits of grid iron system, like valves, then water coming from multiple directions, all those things are same. That means we get all the benefits, but we get even more reliable system compared to the grid iron system. So, it is also used in well planned cities. It's a closed ring or a complete loop, either circular or rectangle of larger diameter, arterial main pipes around the area to be served. So, we have larger diameter arterial main pipes around the area that is to be served. So, we get water from all directions, and it's costly and sometimes placed within a grid iron system or around a high demand area or loop feeder. So, that means within a grid iron system, we can, if I just go back, we can see within this particular area, I can design a system which is following that loop system. So, in this way we can also design that. So, a certain section of a grid iron system could be designed in this particular way. So, similar to this one, there is another, you can say that in radial system, the difference is within this particular, see it looks more or less same, but over here we have the main. From the main we supply to the different overhead reservoirs which are located at the central part of the zone, and from there we serve the water in all the different directions. So, this is another way, but here also sort of a loop is formed and we can serve the water to this in all the directions, and water is actually coming from multiple directions. So, water lines are laid radially outwards from the overhead reservoirs, and this because these are centrally located, it ensures high pressure and efficient water distribution compared to the other systems. So, finally, we come down where we take a look at the different kinds of valves that are used in distribution networks. And as we discussed earlier, that we use isolation valves like this one, or slice valves, where we allow system isolation for repair and maintenance. And this kind of valves are spaced at certain intervals, particularly in 12-inch diameter mains. We see them at the interval of every 1000 feet, or whenever there is a node. I was showing you that there are 3 valves in that each node. In case of meeting of mains, multiple valves, preferably 3 should be used, and all branches from an arterial main should have an isolation valve. So, this is the principle based on which valves are provided in a distribution network, and you can see the image of a valve. And in addition to this isolation valves, there are other valves involved in a distribution network, such as air relief valve, backflow prevention device, pressure reducing valve, and so on. Now, the purpose of a air relief valve is, as you can understand, water, in particularly if it's a dead end system, if it's an intermittent supply, or sometimes air gets into the pipeline, and because it's empty, of course, and then when you send water, sometimes these pockets form and the water cannot travel. So, there has to be a mechanism to release that air pressure, right, or the air that is trapped inside the pipeline. So, that is why we use a air relief valve. So, you can see the design of air relief valves over here. So, there is a float. When there is water pressure, this float raises up, and then this opens up, and this extra air over here can be released. This is the actual image of this air relief valve. And similarly, we have a backflow prevention device, so that water cannot flow back inside the system. That means it only moves in one direction, it cannot come back. So, this kind of a devices are used. And then there are pressure reducing valve. If in some places the pressure exceeds, there could be many reasons for that. Maybe a pressure reducing valve would be able to take care of that. So, these are the different valves. So, to conclude this lecture, we can say that gravity based water distribution system are more efficient and reliable, and when possible we should go for gravity based system. Zoning is an iterative exercise till the hydraulic performance is optimized or acceptable for an area. Then velocity range within pipelines are fixed, and size of pipelines depends on the peak demand. And finally, distribution system layout for a city can be a mix of different systems. It does not need to be only one, it can be a mix of different systems. So, these are the references. Thank you.